welcome back. So this portion will be on the final portion, which is after we have actually prepared the data, we will actually train the AI model. So we'll go back to Azure Machine Learning Studio later, but we'll first start with the slides first. So after the previous step of splitting the data, the next portion is really to do the training, which I have mentioned before. It's actually the most straightforward part of this process. So what you need to do is actually to add in this particular widget called the train model. Just search for it, drag it in. Now you need to connect the the right input port to the training data. So take the training data, connect it to the right port, which is actually the data port. And for the left port, you need to connect it to a learning algorithm. Whatever machine learning algorithm you want to use that. So for this particular exercise, we will use a very classic learning algorithm for classification called the logistic regression, a two-class logistic regression. Now, despite the name, actually, a two-class logistic regression is actually a classification learning algorithm. It's not actually a regression. It's only named logistic regression for historical reasons. So you will see that there's actually an error because it doesn't, just like the filter-based feature selection earlier, it doesn't know what is the output or target variable that you are trying to predict, right? So it has all the columns of data, but it doesn't know out of all these columns of data, which of the columns is actually the target variable. So you need to select this train model, go to the column selector, and then basically select again whether or not the person has donated blood. Click on the right button, select that, and then just click on OK. And the other thing that you actually need to add after you've done that is actually to connect the two-class logistics regression, which you can just search for it. Just look for logistic regression. Actually, there's two versions of it in the Azure Machine Learning Studio. One is the multi-class, which means that it's for more than one possible output. But in the case of our model, it's a binary case. There's only 1 and 0. So we would use the two-class logistic regression. So just connect it to the learner port, which is actually the algorithm that you want to select. Now you can actually choose different algorithms. We have only chosen this as an illustration to show what you can actually get with a very classical, very well used logistic regression algorithm. This is actually one of the most popularly used algorithm because it can handle very large volumes of data, and it gives you very good explanation of how the decision is made, and also gives you some estimation of the likelihood that the answer is actually correct. So it's probability based. So instead of just giving you yes and no, it also tells you what's the likelihood of yes or what's the likelihood of no. So that's the other advantage, right? So it gives you some amount of certainty rather than just the answer by itself. So for some applications, like in medical diagnostics, you don't want to know just that whether the patient will be deceased or die, but you also want to know what's the likelihood the person will actually die, right? So that you do not want to just reveal this information without knowing at least the estimation of the likelihood that event will actually happen. So once you run it, you will get the all the green OK symbols, which is actually everything is created. And the model, which is being generated, the model, let me repeat again, is actually the program or the rule that's automatically learned from the training data. The test data is not shown to it, so only the training data is presented. So the learning algorithm that we apply is the strategy to learn from the data. So when we apply this learning algorithm to the data through the train model widget, the output port will basically contain the trained model, which is the rules that have been learned from the data. So that actually is the output that we're interested in to actually save and actually deploy into our application itself. So you can actually visualize, right-click the output to just take a look at what the output is like from the trained model, which is again the learned rules, right, from the data itself. So for the logistic regression, the parameters that can express what the model is actually very simple. It's just a series of weights, just like the neural network weights that we talked about earlier, but these weights are related to the logistic algorithm. So they have interpretations related to the logistic algorithms parameters. So the first set of parameters when you visualize is just what we call the hyperparameters. It's just like the k value in the k nearest neighbor. Is some values that can be used to adjust how well this algorithm works with the data. So we just took the default values earlier. So these are the default values. The more interesting ones are the feature weights below. So the recency, each of the columns has a certain weight associated with it. And you can also see one additional column called bias. Now, bias is actually an interceptor. If you remember your secondary school mathematics or your high school mathematics, if you have a linear equation in the form y equals to mx plus c, the m is important because it gives you the slope. How fast is the y value changing when x changes, right? The m is the slope plus c, but the c value is actually just an adjustment figure. Okay, it will adjust where the line, the linear line is within the x axis. So you wanted to adjust it higher, you have a higher c value. So this bias term is also similar. It's actually the y-intercept. It is the adjustment figure to just move the curve into a region that is actually where all the data is currently located. But it doesn't have any particular meaning other than as a mathematical adjustment figure. The ones that have meaning are actually the weights that we see here. So for logistic regression, a larger weight means that that particular predictor is actually better. And if you remember our feature selection earlier using chi-square, this is actually the same, right? Because this is actually the largest value. And from the chi-square test, we know that actually recency is the best predictor as well. So at least for the logistic regression, it actually tells us the same information, that the most important predictor is actually the recency. Large negative values in the case of logistic means that larger recency values, that means it has been a long time since the last time the person has donated blood. If it has been a long time, the negative value means that it's a tendency or likelihood towards the zero value, right? So I'm explaining to you the interpretation because I understand the theory of logistic regression. So you want to see how this is actually done, you need to understand the theory behind that particular algorithm. So the interpretation requires you to have some understanding of the theory. So negative values means a tendency or a likelihood towards zero as the output. So large negative value like this means that actually recency is a good predictor, but larger values of recency is associated with zero as the output. Now for frequency and monetary, they are not as high as the other one, but they're also not too low. They're close to 1, but they're positive, which means that the larger values for frequency is associated with the output of 1, which means that if I actually donate blood more frequently, instinctively you also know this will be the case. If I donate blood more frequently, it's more likely that I will actually be a blood donor again in the near future. So this pans out. Large positive value means that this is an important predictor as well, but positive value means there's a tendency towards the output of 1. That means this is a responder. Higher frequency corresponds to higher likelihood of responding to the blood donation drive. Similarly, monetary is almost identical values, right? Maybe it's different by the trailing digits, we don't know, but as far as these two values is identical, because monetary, just like frequency, the larger the amounts of blood you donate, the more likely you're going to donate blood again. They're actually closely related after all. Okay, so if you have actually donated highest amounts of cc's of blood, the logistic regression tells us that yes, that will help us predict whether or not you respond. And because this is a positive value instead of negative value, larger cc's of blood corresponds to a more likelihood of a 1 as a result, not 0. Negative is associated with 0, but positive is associated with 1. Okay, so we can actually save this model so that we can use it later. So I'm going to just right click and save the model, give it a name, so like blood transfusion logistic, and then click on yes, and then it will save it. So next is actually whether or not that model that we've saved is actually good enough. So I mentioned before, actually what we're interested in is the train model that we just saved, but I'm not sure if what has been learned by the train model actually corresponds to the intent that I have, and that is actually it learns the trend of how frequency, monetary, and recency values actually related to the tendency to donate, or is it overfitted? So we need to actually do an evaluation or test that the result, that whatever predictions I get from the train model is actually working well with the test set. Because if it's not working well with the test set, it means that basically it only works with the train set. It's not likely to work well with future data that I have. So that model can't be really used. So what I actually do is I would introduce a new predict model or score model. So this function actually makes predictions using the model you feed to it. Okay, it will make predictions. That means you try to predict what is the Y value or the label that's associated with the input data. So you give it the rule that you have learned. You give it the test data that you want to test against. Okay, so just now we have trained the model with the training data. Now we are going to actually test it with the test set rather than the training data. So with the train model and the test set, it's going to apply those rules to the input test data, and then it's going to be able to predict what the corresponding response rate is going to, the response likelihood is going to be, right? Is the response going to be a 1, or is the response going to be a 0? And it will create a new column called the scored label for those predictions. So ideally, the scored label and the actual label should be the same. That means your prediction is spot on, right? It's always accurate. Whatever I predict as the scored label, the predicted label is always the same as the actual label itself. So when you do not need to indicate a column for the score model, it already knows what is the target variable from the train model output itself. So you click on run and it will run. Then the next thing you need to do is actually to output to compare the scored label with the actual label to see how many percent of them are actually the same. So one of the widgets to help you do this is actually the evaluate model. So you can, of course, just compare yourself with your eyes, right? Just compare the two columns. But if it's the 1,000 rows of data, it will be very tedious. And if it's 10,000 rows, you're most likely going to make a mistake anyway. So instead of doing it with your eyes, there's an automated tool for you. It's called the evaluate model, and just like the score model, I don't really need to select the output parameter or the target variable because it already knows that from the train model earlier. Okay, so once you run it, you can right click on visualize to see what's the result from the evaluate model. And this is the thing that you have. The first value that you have is a graph like this. It's called the receiver operator characteristic graph, or the ROC curve. And it's actually a plot of the performance of the classifier with different ranges of data. Okay, so based on the true positive rate and the false positive rate. Now, normally when you just calculate the accuracy, you're just getting one number over the entire data set. But actually, the performance may be varying when you actually look at different portions of data. So some portions of data may actually give very good result, but other portions of data may be very bad. So in order to give us a graphical view of how consistent is the performance, we actually plot a curve like this, right? If the classifier is actually or the model is actually very poor, it will be close to this gray diagonal line, which represents random guessing. This is basically a random toss of a coin. So you're just randomly guessing. You have a 50-50 chance of being right at any point, no matter how much data you use. This is just random guessing. So if the blue line is actually very close to this, it means that your whatever model that you build is just slightly better or just about the same as just randomly guessing. So you might as well not go through the effort of building the model, because tossing a coin or randomly guessing will actually essentially give you the same result as well. So the ideal case is actually that this blue line should actually rise like a rocket to the top to 100% and just stay at 100% all the way to the end. So it should actually look like a square. So one of the measures of how good it is actually is the area under the curve, right? So if it's the worst case, it will be 50% because it's a triangle of a 1 by 1 square. You can see that the axis is 1 and 1. So half of the height and width is actually 0.5. So that's actually the worst case. And the best possible area under the curve is actually a area of 1 because it's a square. So this particular area under the curve is probably close to 70, 80%. If you look at the shape of it. And it's not very smooth because there's not a lot of data. The more data you have, the smoother the curve will be if the classifier is good, because there's not a whole lot of data. But yet it is actually not so rough that we could actually throw it out. It's fairly consistent, right? As I give it more data, it will actually approach the 100% mark in a smooth manner. If you look at the bottom of that portion, and I'll show you the result from my web interface data, you'll find that there's an overall accuracy, and these are other metrics that you can actually get. So the overall accuracy is about 78%. So although this is not an ideal classifier, the results can probably be used if we can check against the train set and check whether or not there's some overfitting. But I will not go there. That's something that you will probably want to do in a live project, but this is just a demonstration. So the indication here is that the test set at least gives me 78% accuracy. So it's not too bad. I can probably use this particular classifier. So the train model that I saved earlier has been evaluated, and I deem it to be good enough for me to use. Okay, to actually deploy onto the web service, and probably in the interest of time, I'm probably not going to show you on the web interface itself. All you have to do is actually to create a new experiment, and also to drag in the model that you saved earlier from the train model section, and you can also find it in here under train models. Bring it into the new experiment, put the score model, and then actually pass the original data in to the score model. Now, the data won't actually be used in the building of the web service itself. It's just used as a template to know what columns of data are available. So once you click on all this connected, you click on run. And you can find that after you run it, all goes, yeah, it's all green tick. You can then click on set up the web service. When you click on that, it will generate 2 nodes for the input and output section, right? And you see that the blood transfusion is actually grayed out. So next is actually just to run it to get the green tick again. And once it's all green tick, you can actually click on deploy as a web service. It's not enabled now because you haven't clicked run. So once you deploy, it will be live, and you will have an interface that's like this that actually tells you some applications, mini test applications that you can use to just test the web service. It's live, and it's literally just one click, right? You click on deploy web service, this button, after you run it with the green tick, and it will become live on the Azure internet. Azure portal. So one button to just click and deploy your train model. Very convenient. So what is the negative parts about this particular service? You cannot export the web service. So whatever service that you build, it is generated for you, is saved for you, but it can only be deployed on a Microsoft cloud. After all, this is a free service provided by Microsoft. They don't want you to take whatever has been generated for you and then deploy it on Google, or deploy it on Alibaba, or some other cloud provider. So whatever you build stays on the Microsoft cloud. Same for the train model as well. You can't actually export the train model. It has to stay in the cloud. Not only the service cannot be exported, but the train model cannot be exported as well. But what you can export actually is that if there's some output that's generated, like the score model has generated some predictions earlier, I can actually export the predictions, right? So, but the model itself cannot. You can only export the results or the input, and you can import new data, but you cannot export the core, which is the trained model itself, nor the service. Okay, so to use it, just click on the test, and then you can actually just enter some data, and it will actually give you the predictions like this. Okay, so that, and whatever service you've created, it will be actually one of the services within the web services tab that you see there. Right, so that comes to the end. So I'm going to switch over to the web interface now and just show you how to do that modeling very quickly. But the deploy part, you will have to try it yourself because I don't have the time to do that. Okay, back to our experiment. The last step that I showed you earlier was the split data. So what we need next is basically to train the model. So I'm going to just do a search for train model. Select it with the left mouse button and just drag it onto the screen. And now there's an error here, but I'm going to set the results, the train set onto the right port. And then I'm going to basically select the widget and say, tell it which is the target variable. And click on yes. So they're selected. And once it's selected, what's missing is now the learner. So I'm going to have to do a check for logistic regression. So I'm going to, there's actually two. And because this is two class, it's actually more efficient to use the two class logistic regression. Select it. And then once you select it, it has the algorithm, it has the data, so the error goes away. So now I'm actually just going to run it to show you what's the result of this. Okay, so let's take a look at the train model. What does it look like? Right click, visualize. So you can see that actually the first part is just the hyperparameters, and then the weights just now that was mentioned in the slides. The larger the weight, the more important is the predictor, is a better predictor. So recency is actually the best predictor value. No surprises, that's because that's exactly what the chi-square test also told us. Frequency and monetary are worse. Now it depends on the importance that's actually obtained from the algorithm. It depends on the algorithm because some algorithms may favor certain parameters, certain features more. Remember earlier on in one of the earlier lessons, I talked about the machine learning playground, and I show you that for a decision tree, it tends to create these rectangular regions, whereas if you use k nearest neighbor, it will just give you a diagonal line. So every single algorithm in machine learning has certain assumptions they will make about the data. So what it will tend to favor as the most important predictor really depends on how the algorithm works, right? So even though chi-square itself, the test also makes certain assumptions about the data nature itself. So, but at least for this case, the logistic and the chi-square, they have similar results. Right, so this looks okay. And then the next thing I want to do is basically to save this model. So I'm going to save as a model, and I'm just going to give it a name of blood donation logistic regression train model. Give it a name. So we know blood donation logistics. So we know the source data and also the algorithm that was used to build that model. So it's useful to name your models with the algorithm because the same blood transfusion, blood donation can also be used with decision tree. So I will save my model as blood transfusion blood transfusion decision tree, right? Result of logistic regression. So I've saved it. So you can actually go to the train model tab and you can see that whatever is saved is actually there, right? So remember to save before you transition, otherwise you lose the work, your work. Let's go back to experiments, and if I click on it again, yeah, we'll find it. Now you can see that my mini map is actually useful for me to very quickly move to where I want to, which is at the bottom section. Okay, so what I want now is actually to evaluate. So I have already saved the train model, which is actually the output that I want from this whole process, right? So the idea now is really to check if the model that I just saved is actually good enough for me to use in the real case. So to do that, I need a score model which predicts values using the train model. And you also need to give it the test data. So use the train model and the test data, and we're going to run it first to show you what it does. Well, notice I do not need to select the target variable. Now, if I right click, I can actually save as a data set and I can actually export out the output as well. So I mentioned just now that you can actually export the output. You can import new files, but you cannot export the model. Okay, that's the only thing you cannot export, as well as the service that you build or web service that you build using the model. The code cannot be exported. So I'm going to visualize the output from this already done. So now there's actually two new columns, right? So you can see that the original label or target variable is this, but there's now a new one called the scored label. This is actually the predicted value for the label, right? So if it is actually a non-donor, I actually predict in this case that this based on these values and the trained model I have earlier, I also predict that this is a non-donor, because it's probably because the recency is rather large, right? It's not just one or two, but it's larger than 10. So it's likely that when it's a large, remember it's a negative parameter, right? So it's larger values of recency is associated with 0. So I predict that this is going to be a 0. And the next one as well. So most of these are the same except for this one where it's actually a 1, but I predicted it to be 0. So there's an error here, right? The predicted value doesn't correspond to the actual value. So how many of these are there, right? So that if all of them are the same, it means that your accuracy is 100%, your classifier curve will be, your ROC will be actually a perfect square, but there are some, there are actually errors or misclassifications, so that is why the accuracy is not 100%. So this is one column that actually tells you the predicted label, the predicted Y or target variable. The second one is actually the output or the certainty or the probability that the value that you have predicted, what is the probability of it being a 1? So the probabilities are calculated relative to 1. So it looks like the value is very low because the maximum probability is actually 1. But because this is calculated as a 1 probability, so it's because my output is actually 0, it's actually not 19% certain it is 0. It's actually 19% certain this is actually associated with 1. So 100% minus 19% is actually 81%. So it's actually quite certain it is a 0. So you need to subtract, for the case for 0 outputs, right? You need to subtract this value from 1 to see how certain it is actually is a 0. Same for the next output as well, right? All these are all 1 probability. The likelihood or the probability is actually 1. So it's actually very low because the output that is predicting is actually 0. So as you can see that some are actually more certain. For like this is quite certain that it's actually it's 90 close to 90% certain, because 1 minus this value is close to 90%. Certain that is actually 0, whereas for some of it is not so sure, right? It's this is more like 70% sure that it's actually a 0 as compared with this one. So the certainty does vary, right? Some are more certain because of the range of values that you have. So the trend basically gives you an indication of how well it fits the decision boundary that you generate using the logistic regression. And that tells you what's the probability. Remember, for the logistic regression, it will actually generate a straight line for you, and the distance from the line tells you how certain you are, right? If it's exactly on the line, it's just 50-50. It's basically maximally uncertain, but if you're further away from the line in either direction, you're more certain it's either a 1 or a 0. Okay, so but if you look with our eyes, just now we have like 200 rows, but there are always over 700 of them, 100 over of them, right? So we're not very sure. So we're going to use the evaluate model to just automatically check every single one of them to see if it is actually correct. So let me just click on this, and then if I run it, right click and run, I actually find that it's okay. Let's save for sure for the good measure. Now, if you look at the visualize the evaluate model now, the first part is the ROC curve that I mentioned before. So the 45-degree line is the maximally uncertain line, right? It's a random guessing line. And the curve here is actually some distance away. So it looks like it's quite a reasonable classifier, something that I can probably use. And the overall performance actually 78%. But I'm not very certain if there's actually overfitting yet. So I need to actually have one final test, and that's actually to check if the performance for the test set is similar to the performance for the training set. So to actually check that is very simple. You can duplicate the score model, or I can just pull in the score model again. So I need another widget with the score model. And in this case, I'm going to just reuse the train model. I don't need to do the training again. But instead of using the test set, I'm going to use the training set. And I'm going to use the second chord in the evaluate model to compare. So I'm going to do a run it. You notice that the run below actually runs everything. So just one single widget. So the first original line is the blue line. Now this is going to generate a second curve in the ROC curve graph, which is in red, which is actually for the train set. And if it's not overfitted, both of these actually should be very close to each other. So you notice that actually the red line and the blue line are indeed very close to each other, and the red line is generated from the training set, which means that it is going to be smoother since there's more data in the training set, what I mentioned to you earlier. Whereas the test set, the blue one, is a bit more jagged, but they are actually quite close to each other. In terms of the overall performance, we know that the blue one is 78%, whereas the red one is about 77%. So they are only about 2% difference. Now, you do not expect these two values to be exactly the same all the time. There's bound to be some amount of overfitting in any machine learning model. But if it's within 10%, typically we will think that, hey, this is actually an acceptable range. You cannot expect it to be exactly the same, because there will always be errors in the data or noise in the data, some difference from what you normally expect. So, and you have less training data than test, you have more training data than test data. So definitely the performance will be different. And imagine actually it's guessing using the model that has been trained to learn the rule, but it's guessing the result for data that it's never seen. So it's quite amazing that in fact they are actually the same, right? Because it's never seen the test data before. So if you can give similar results for the test data, we know actually when we see new data in the future, it's likely that the result will also be very similar. So the test data is actually stand-in or proxy for future data that we might have. So we actually come to the end. So this is actually just to show you that you can easily do it yourself. No coding is involved. You just need to be able to log into Microsoft Azure Studio. It's a very good prototyping tool. It's very good learning tool as well. You can just try it out for yourself. And it's free of charge, costs $0 for its use. The only thing that you would be have to be a bit careful is that maybe you get hooked onto it and you will actually want to use the service from Microsoft, from the paid service, where it has gives you some greater guarantees of service. So with that, I thank you and I will see you in the next series of videos.